For the alkaline fuel cell system, we have a number of main components. If you look at the system design here, we have the anode, the cathode, where we have the catalyst to drive the reactions, and then we have the electrolyte. If we start out with the electrolyte, where we have the OH ions moving across, the typical electrolyte that we use is aqueous potassium hydroxide, but other hydroxides are used as well, but potassium hydroxide has the highest conductivity. The concentration of aqueous potassium hydroxide that we use is typically in the range of 30 to 40% at low temperature. At these temperatures, at these concentrations, we have the highest possible conductivity. But if we want to operate the system at higher temperature, where we risk evaporating water off, we typically use higher, up to 85% of potassium hydroxide concentration. The typical operating temperature for the electrolyte and the alkaline fuel cell system as a whole is between 70 and 90 degrees. But a new design has been proposed where you can go all the way down to room temperature, which simplifies the system significantly and also reduces corrosion from the relatively corrosive potassium hydroxide. There are two main electrolyte designs in the alkaline fuel cell systems. Either the potassium hydroxide is immobilized in some sort of matrix, where the two electrodes are then bonded to either side of this matrix. Historically, the matrix has been made out of asbestos, but now a material called siphon is primarily used. The other main design is a flow-through system, where the electrolyte or the electrode acts as barrier for the electrolyte, and then you flow the potassium hydroxide through the system continuously. So you basically circulate it in between the two electrodes that you have. There's advantages and disadvantages to the two systems. The immobilized system is relatively simple and similar in design as what you would see on the PEM fuel cell systems. Whereas the potassium hydroxide with flow-through, you can use the circulating electrolyte, you can cool it or heat it, so you can cool and heat the system in this, and it's possible to achieve higher efficiencies with this system. But it cannot be as compact, since you would need a certain distance in between your two electrodes in order to have a proper flow-through of materials. If we look at the anode and cathode catalyst that we have a number of different catalysts to choose from. And basically we try to choose based on activity of these catalyst materials, stability for the duration that we have specified for this specific system, then the cost of the catalyst, and how readily available they are. And it's difficult finding materials that are high on all of them. So we basically have this matrix of available fuel cell catalysts in the alkaline system. Well, it can be platinum. The same goes for the PEM fuel cell system, where we almost exclusively have the platinum-based materials available. Other material has been suggested, but not with as high activity and stability. But in the alkaline system, we can get almost as high activities and stabilities with nickel-based materials and different kinds of oxides. So we have more catalyst materials available. Actually, we have a second dimension on this graph, basically the reduction and oxidation reactions that we have, but there's a lot of overlap. So typically the material that are good catalyst for the oxygen reduction reaction are also good catalyst for the hydrogen oxidation reaction. And for the alkaline fuel cell system, the main advantage is that you can use nickel-based catalyst, so they are very widely used. And due to the lower cost and favorable activity, it is the main component or the main material that we use for this type of fuel cell system. There are some issues with potential deactivation of nickel through hydride formation, but that can be worked around by different types of coatings with iron or alloying with different kinds of compounds, and it's relatively known technology. So when you have the catalyst, we form them into an electrode. The way that it was originally done by Bacon's design back in the 50s was with the mixed porosity of the nickel material that you had. So by mixing the porosity, he could achieve a separation between the liquid electrolyte phase and the gaseous phase at the cathode and anode through capillary forces, simply by mixing the particle size or the pore size of his different materials. Today it's typically done, the catalyst is a nickel mesh that is then mixed with PTFE binder and rolled onto to this mesh. So you have the PTFE acting as the barrier on the gas side, so it allows gas through but keeps the liquid electrolyte on the electrolyte side. And the design of them are typically as shown here in this graph.